every matrix has 4 subspaces of some Euclidean space associated with it. These subspaces are called the row space of the matrix A, which lives inside Rn. The row space is just the span of the rows of the matrix, and since a matrix has since the rows of a matrix have n entries, this span is going to live inside Rn. There's the column space of A, which is just the span of the columns. And since the columns of the matrix A have m entries, this span is going to live in Rm. And then there are 2 more. There's something called the null space, which is basically, if we think of a matrix as a linear vector function that goes from Rn to Rm, the null space is just everything that gets sent to 0 by this linear vector function. Remember, this linear vector function acts by just multiplication, right? That's how we turn a matrix into a linear vector function. So the null space is just everything that gets sent to 0. And then there's the image, which is actually, if we have this linear vector function, it's everything in Rm that gets hit by something in Rn, right? It's possible that not every vector in Rm will have something that goes to it. So every vector in Rm that does have something that goes to it is in the image. And it turns out that these are actually all vector spaces. So let's look at these in turn. We'll look at the row and the column space first. So for the row space, right, it's just this, if we name all the columns A1 through AM, then the row space is the span of all the rows, which lives in Rn. And it's actually a fact that these elementary row operations that we have done to solve linear equations, these row operations don't actually change the row space of the matrix. And that's not totally obvious, but it's not that hard to prove either. So first of all, remember we have a row operation where we interchange 2 rows, right? So what will that do to the row space? Well, the row space before the change is, let's see, it's the span of all the rows. So there's going to be IA as one of our rows and IJ as one of our rows. And then, so this is before. And then after we make this change, after we do this row operation, the span is the span of, let's see, all the rows, and then AJ shows up, and then AI, because we just switched the 2 rows, AJ and AI. But, the span doesn't care what order these vectors are in. It only cares what vectors actually appear in these lists. So since it's the same vectors in these lists, these 2 spans are clearly the same. So nothing really to prove here. These 2 collections of vectors are the same, even though they're in a different order. So interchanging rows doesn't change the row space. Okay, let's think about multiplying a row by a column. So before this operation, our span is just all of the vectors, or all of the rows, including A sub I. And then after this row operation, we're taking the span of all the rows, but we've replaced row I with C times row I. And remember, C isn't 0. Okay, does this change the span? Well, if you look at what all of these linear combinations would look like, so it's going to be little a1, right? Little a is a coefficient, so little a1, row 1 plus, and so on, all the way up to little ai, row I, and then all the way plus, all the way out to little a, I guess it's m, row m. And then after, linear combinations of all of the rows after the operation are little a1, row 1 plus, so on, out to little ai times c a I plus, and so on, out to little a m, row m. Well, you can see that these two lists of linear combinations are actually exactly the same, because if we replace little ai in this one with little ai times c, we get that one. So these lists of linear combinations are actually exactly the same. Right? Another way to see it is just, well, group these like this and call this little ai. You know, maybe decorate it if you want to, just to distinguish between the new little ai and the old little ai. And these are talking about the same linear combinations. So multiplying a row by a non-zero constant also doesn't change the span. So really the only tricky one is taking some row and adding a multiple of some other row, like this. So before we do this row operation, our linear combinations look like a1 row 1 up to ai row I, and then somewhere further along there's going to be aj row j, and then all the way out to am row m. After this row operation, we get a1 row 1 plus so on, and then row I actually isn't changing, so it's still ai row I, and then plus aj, and then here we have to put the jth row after we do this row operation. Well, after we do this row operation, the jth row is the ith row, sorry, no, the jth row plus c times the ith row, like this. And then so on out to a sub m times the mth row. But if you look at these, right, we can regroup these terms. So we can regroup this. So there's only one term with the first row, so that's a sub 1 times first row, and then so on, right? None of them change until we get to the ith row. And here we have two terms with the ith row in it, so we can factor out that ith row, and the two terms are a sub I and c times aj. So caj. All right, and then again, all the rest of them don't change until we get to the jth row, but the jth row is just aj times the jth row, so that, and then the rest of them are all the same. So a sub m, mth row. Well, you can see that these lists of linear combinations are the same, because here we have first row times an arbitrary constant. First, all these are the rows times arbitrary constants. It's just that this arbitrary constant it's still arbitrary, right? This can still be any real number independent of all the other a's, but it's just sort of written in a funny way. So these two lists of linear combinations are still the same, and so this row operation does not change the span. For all three of these, essentially what I'm doing is showing that these spans are included in each other both ways, and that means they're actually equal. All right, so that's the row space. I guess I should note that the row space of a matrix is actually a subspace, but that's obvious because it's a span, right? Every span is always a subspace. That's sort of, we defined span to make that true. Or we defined subspaces to make that true, I guess, depending on your point of view. Anyway, so here's a matrix. Let's find a basis for the row space of this matrix. Well, we know that if we do row operations, we won't be changing the row space of this matrix. But what could we, so we're allowed to do row operations. That won't change the row space. But what could we do, what can we do by doing row operations? We could reduce this matrix to its row echelon form. If we reduce this matrix to a row echelon form, then the rows will obviously be linearly independent, and that's what we need to have a basis. We just need to somehow find a minimal spanning set for the span of these rows, but one that is also linearly independent. But the rows in a row echelon form are always linearly independent because of that staircase pattern of ones. Right? That makes it so that the rows have to be linearly independent. So we can just reduce this matrix. So let's see. You get to watch me reduce a matrix again. So we can add twice the first row to the second and third columns. So these are second and third rows. So these first row isn't changing. Second row is going to be 0. And then, so we're adding twice. So +1 and -2. And then here we get 0, 0, 0. And then last row we get, let's add 1 times the first row to the last row. We get 0, 3, -6. Okay. Now let's leave the first row alone, leave the second row alone. Third row, I guess leave alone because it's all zeros, and then subtract 3 times the second row from the fourth row, and that's going to give us all zeros. Okay, well, because we were doing row operations, the row space of the first and the last matrix here are the same. So these have the same row space because we did row operations. But the rows of this last matrix are obviously linearly independent because of that staircase pattern in the ones, right? So that means that we can write a basis for the row space. And even though they are coming from rows, I'm still going to write them as columns. Just the non-zero rows. So 1, 3, -3, and 0, 1, -2. Of course, so I stopped at this row echelon form. We could go all the way to reduced row echelon form. That would give us a different basis, but it still would be just as good a basis as the one we found. Notice that when we do this, the number of vectors in our basis for the row space will always be the non-zero rows, but if we've gone to row echelon form, the non-zero rows will always have a leading 1. And that means that the number of leading 1s is the same as the number of vectors in our basis. And so the rank of A, the rank of any matrix, will always be, so the rank is the number of leading 1s in row echelon form, but that's the same as the number of vectors in this basis. And that means that the rank is the dimension of the row space. And that's always true because of this thing we just did. All right, so that's the row space. You can imagine that the column space is going to be pretty similar. The column space is just, right, if you take all the columns of your matrix, take their span, that's the column space. And since this matrix has m rows, each column will have m entries, and so all of these vectors live in Rm. Now, just like row operations don't change the row space, or don't change the span of the rows, column operations don't change the column space. And the argument works exactly the same, so I won't go through that argument. But let's see how it works to find a basis for the column space. Well, just like we did row operations to find a basis for the row space, we can do column operations to find a basis for the column space. So I guess instead of using R's with subscripts to indicate row operations, let me write C with subscripts to do column operations. So let's see. I want to keep this column because it has a -1 in its first entry, which is kind of nice for doing column operations. So let's do column 1 plus twice column 2. And let's do column 3 minus twice column 2. That'll zero out some stuff. Essentially what I'm doing is I'm aiming for that same stair-step pattern because that will guarantee that the columns are linearly independent. All right. Okay, so column 1 plus twice column 2, that's going to give me a 0, 1, 1, minus 2. Column 2 we're not changing, so minus 1, 1, 0, 0. And then column 3 we're subtracting twice column 2, so 0, 1, 2, minus 1. And then column 4 we're leaving alone, so 0, minus 3, minus 5, 4. Okay, so right, I used this minus 1 to zero out the stuff to the right and the left of it. So now we can use this one right here to zero out the stuff to the right of it. And in fact, we really only need to zero out these two over here. We don't need to mess with that one. We could if we wanted to, but why bother? So let's do column 3 minus column 1 and column 4 plus 3 times column 1. So column 1 we're leaving alone, so 0, 1, 1, minus 2. Column 2 we're leaving alone, minus 1, 1, 0, 0. And then, so column 3 minus column 1, so 0, 0, 1, 1. And then column 4 plus 3 times column 1, 0, 0, minus 2, minus 2. I think I did that right. Okay. And now we can use this one to zero out the stuff to the right. We get 0, 1, 1, minus 2, minus 1, 1, 0, 0, 0, 0, 1, 1, and then 0, 0, 0, 0. All right. Now, I don't quite have the stair-step pattern I was promising, but if you just rearrange the columns, you'll see the stair-step pattern. So let's just switch these two. So we get minus 1, 1, 0, 0, 0, 1, 1, minus 2, 0, 0, 1, 1, 0, 0, 0, 0. All right. And now the non-zero columns are clearly linearly independent because of this stair-step pattern. Maybe I should explain that. So if you imagine linear combinations, so taking just the, actually let's start with the third column. If you take just the third column, it's non-zero, so just the third column is linearly independent, but the second column isn't in the span of the third column because the span of the third column always has a second entry 0. So the second column is not in the span of the third column, so when you add that to your collection of vectors, the collection is still linearly independent. So now it's these two columns we know are linearly independent. Well, the span of the middle two columns always has a 0 in its first entry, so the first column is not in that span. So if we add that to our collection of vectors, it's still linearly independent. So you can see how the stair-step pattern is what makes this trick work. So anytime you have a stair-step pattern, you get linear independence kind of for free. So, we've done column operations, so we know that doesn't change the column space. But if we take just the non-zero columns, these are clearly linearly independent because of that stair-step trick. And so this must be a basis for the column space because it's a spanning set for the column space that is also linearly independent. So this is basis for the column space.